Seems like it's working. Hello and welcome back to Calculus 3 on this glorious Monday evening. Right, we are starting a new week, fresh. Everyone is happy as you can be. We're talking about 13.4 triple integrals, right? So we are going a dimension up. And it's going to be the same deal as with double integrals. You will be able to use triple integrals to either compute three integrals, three dimensions, so volume, or fourth dimensional entity, bulk, wow, by placing in the function within. So let's talk about the idea, triple integrals. And we will see that, I could write this immediately so we understand. If I have a triple integral that goes, let's say, from a to b to c to d and then 0 to f of xy dv, that will be the same as if I had a to b, c to d, f of xy dA. So we see the correspondence immediately where that middle integral would just integrate into f of xy, right? Because you have a 0 on the bottom. So calculating triple integrals is the same as calculating double integrals, except now you have to do 3 calculus 1 integrals rather than 2 nested integrals. So we are talking about pretty much same calculation. But now you have this creature dv. So what we had in the past, is it was, this 0 doesn't look too good, and this c doesn't look too good. So here we go, much better. So in the past, we had integral a to b f of x dx, right? And that was calculating area. And what we had was the representative rectangle dx, which was moving left and right. Maybe I should draw that red. Representative rectangle that was moving from, let's say, a to b. And then we had the double integral a, b, c, d of f of xy dA, which was calculating volume. And now we are in the 3D space, x, y, and z. And in this 3D space, we would have some region that was bounded by, let's say, A, and then B, and then C and a D. And that thing was the region R. And what you had there was a representative French fry. If you remembered, so there was supposed to be some kind of surface on top, and then representative French fry would go like this, creating this. dA. So you see that this one has a dx, which is just the width. And then you have dA right there. So now, what's dV? Well, dV better be a little representative cube, ice cube, right? Very, very small, fractions of an inch, going down to nothing, going to 0. So if I have a triple integral with f of x, y, and z here plugged in, dv right? That's going to actually give us a fourth dimensional entity. We call it bulk. And what's happening now is that you have some kind of shape again, but with this you can get a fourth dimensional quantity of a third dimensional object. I can figure out the temperature, the density, and other qualities of something that is 3D. That makes sense? So the three integrals will bind the shape in 3 dimensions, which would put the bounds of on the shape. And then the function inside is temperature, so you can see, how hot certain parts are. Could be density, could be concentration, right? If stirring liquids and stuff like that, so fluid dynamics. There's a lot of application for all that stuff. Otherwise, it wouldn't exist. So we clearly build this up from 1 dimension into 2-dimensional area, into 3-dimensional volume, into 4-dimensional bulk. And just extrapolating in mathematics, you can go to any number of dimensions, even though we have no application for it. So right now, we are going to have some kind of a 3D shape, and what we are going to have is a little is a little cube, which is your dV cube. And then you stack them together. You know how you can put cubes together right next to each other. So the next one will be, there will be 1 cube surrounded by 6 cubes on each side, right? And then corner cubes and so on. So I think, oh yes, the textbook. I'm going to flash real quick. Page 995 has the image in a textbook that it's nicely. You see the stacking of the cubes, right? Now these cubes don't have to be. First of all, they don't have to be cubes, right? These sides don't have to be for purposes of a proof in mathematics. You don't have to have them all the same length. You see, none of them actually are in this picture. But for simplicity, you can think of them as cubes with all the same size. If you want to compute stuff, obviously, why would you use different size? And you stack them all up, right? And by hand calculation, the approximation and everything works the same way. You will be able to plug stuff in. Riemann sum works again, so the entire proof is now just plus 1 dimension. And you see that if this is a flat plane, you know how, let's say, you look at the side of a pyramid, right, in Egypt. And when you're looking from far away, it looks smooth, but when you go closer, you see the blocks and you see it's not flat, right? So that's technically this thing. And the smaller the blocks are, the better resolution you get, right? So better approximation. So if these blocks as dV, if they go to 0, they turn into point-like objects, which gives you the exact, right? They stack into exact shape. So again, the same idea as dx getting smaller and smaller, so those rectangles getting closer to being a line, right? And again, the areas to cover in between and so on. So the proof and everything just goes up 1 dimension, and you are getting the same integral as before. Calculation-wise, you are getting, again, the same, calculate the inner integral first, then the middle one, and then the outer integrals. So they all go the same way, like double integrals. In terms of types, we have, again, rectangular region, and we have general region. Rectangular region means that you are on some kind of a box, so you'll be integrating, let's say, in this room, which means you can swap the order in any way you want. Where the general regions, again, we've seen the last time or last week, that general regions you can't swap easily. In some cases you can't swap at all. In some cases you have to put some additional work. So we have A, B, C, D, E, F. This is all numbers for some function x, y, z. And then you have your dv. So that's the general region. And this dv now could be dx, dy, dz, or any combination on order that you can get. Oops, vd, dv. So you can have dy, dx, dz, and you have 6 of them, right? So there are 6 ways in which you can arrange this dv. So that's general region. General, no, sorry, not general region, rectangular. All limits are numbers, comma, we can swap. Here, easy, right? Easy. So we can swap easy. So that's our rectangular. Now we are clearly more interested in the ones that are giving us weird shapes, which would be general ones, where you have integral over region R of the function x, y, z dv that would work out to be ab, and then you have 2 inner integrals, and then f of x, y, z, and you have dv again in one of the 6 configurations. Now I'm going to actually use configuration dz, dy, dx because I used a and b on the outer, right? And we like that to belong to dx. And then we have dy. Well, dy is the middle integral, which means that the functions inside would be g of x to h of x, because they're only allowed to be in terms of x because x is going to be integrated last, where the capital G can be in terms of x and a y, and capital H. So those are the most inner function. And this is the most interesting integral for us because it allows for all kinds of crazy calculations. This is general region. Cannot swap. Easily. Easy means easy, right? That's how you spell it. At least you spell it when you dominate someone, you can't spell it. Just type easy, that's it. I think. The other way. So now I can't show this on stream, unfortunately, but since you're in class, you get to see it. So behold a 3D object, and when you look at this object is entirely described by the 3 integrals. So its shape and the volume it contains is described by the 3 integrals. The function that it's in there is some kind of quality of the object. It doesn't impact its shape, it doesn't impact its size or volume, anything. That's 100% contained. So the volume and the shape are 100% contained within the three integrals. So if you take the shape and you put that on the xy plane, which is the xy graph, which is on the floor or desk, right? It's the horizontal surface. You put the z-axis maybe through the middle or the side of the object, it doesn't matter. At some point you will have the x-axis stick out of the object, and that's going to be your dx from A to B. So if this is if I have the round object here and I'm holding a cylinder, right? So if I poke z-axis through the middle through the center of the bottom circle of the cylinder, then the x-axis will go across, and I would go from -1 inch to +1 inch. So these limits would be A and B, -1 and 1, given that this is 1 inch to either side. And then this object, right, so that's my dx, then I have to have a dy, and in this case we can see it's a circle, so it will go one hemisphere from the bottom to the top hemisphere, which is what we draw. So the first two integrals, the way I have the red formula is the first two integrals actually draw out your domain. And then the big G and the big H are the shape of the z function on top, which is your h, and the shape on the bottom. Now bottom is just flat plane, and if it sits on the surface, then that's just 0, z equals 0. But this could sit, if you think about the floor is z equals 0, this desk is z equals 3 feet, right? So you're thinking about this desk, you have the object now sitting at z equals 3, which is the flat plane. Your ceiling is equals 10, right? So since it's flat surface, it's going to be capital G equals 3 if this cylinder sits on the desk. And then the top is whatever function is given to you. It could be 9 minus x squared minus y squared, which would be parabola. So technically, you can take the umbrella, right? Figure out what is the equation for the paraboloid you have on top. And then if you cut off the handle, you put that on a table, right, which is 3 feet tall, you would have 3 to whatever the hell z equals paraboloid is, and that will be your age, the top one. So anytime you pick up an object of any shape, it doesn't matter what it is, could be the mouse, right, could be whatever. Now this would be terrible to, the functions for picking up headphones, right? But whatever shape you pick up, it is always going to be the top of that object is the capital H, and that's z equals blah, blah, blah. The bottom, which could be, right, also some kind of shape. So you have two z functions, z of the bottom, z of the top. Those are the capital functions. And then you have the first two integrals, which do that shadow, if you remember from last class and the class before that. The shadow, when you shine the light onto the object, the fattest portion of that object shines the domain on the xy plane, and the shape of that domain has to be captured somehow with the first two integrals. Again, the book does a pretty damn good job in describing. So here you have some kind of, I don't know, this is not really like a capsule or a pill, but I really don't know what this is. It's a cylinder, but it has those round edges on top, and they're crooked too. So you shine the light on top, right? Click. It will shine and it will create a shadow on the xy plane. That shadow on the xy plane is your region R, which could be composition of whatever functions, and those will be your first two integrals. And then the top, which is orange, is going to be capital H, which is the top function, and then capital G, the blue one, on the bottom. So those go into limits, and then whatever the hell you're computing inside, density, temperature, whatever it is, that's going to be the function that goes there, right? So it shows how that, you know very well that as you heat an object, you apply fire here, let's say this is something that is not going to melt. Let's say it's made piece of metal, and you take and you put the blowtorch right there. You can still hold it here for like 5 minutes, right? Because it will take time for temperature to transfer, right, to the object. So that function that does that goes there, right? So because it operates in terms of x, y, and z, it tells you how fast it's going to go up. So this describes the shape, and this describes whatever the hell you're talking about in terms of that shape, right? The quality, some kind. So those are that's how all of this works. And as I said, calculation-wise, the inner integral first, move to the middle one, move to the outer, make sure you get a number at the end. And when you're setting up, if you end up with any variable on the outer integral, you're doing it wrong. That's how it goes. Yes?
So when you're doing like each interval, like the inner one and the outer one, what are you finding in the middle? Like if you integrate h from g of x, y to h of x, y, what exactly is that?
Well, you will still have these two.
Yeah.
So this, and you integrated only one, right? So then the next one is the volume.
Yeah, but what is the one that we just integrated? Like what is
nothing?
It's nothing?
Yeah, you have to wait for the whole thing is done, right? I think of it as this is art of mathematics, so really until the artwork is not done, you want to have a finished painting on the wall, not just a few smudges that are to be amazing artwork, unless you just call it. But you know, the idea is, yeah, you don't actually have anything in that case, because if this is some kind of density function and you just do this, yeah, it's only one dimension integrated. That's a really, really interesting question, but I can't associate it to anything, actually. It's just what it is at that point is incomplete work.
So you're just asking about the A to B? What exactly that entails? Yeah.
No. He said, what happens when you take this temperature over here, you integrate only this? What does that represent before you do this and that?
It represents the double integral.
No. What's left is the whole integral of some stuff there. So eventually, right? So it represents the volume still, right?
So it wouldn't be like the temperature over the z function?
Not really, because you still haven't given the shape, so we don't know how it moves on the outer, right? Because the fatness of the object is your first two integrals, right? The inner integral is just if you put the skewer through this, it will be that point to that point on the top without having the fatness of it, right? So I don't know the behavior of it at all, because there is no fatness for stuff to move. That's how I like to think about objects, right? They're fat, that takes space, and taking those first two integrals out, right, which give the fatness. Going in one dimension, I really can't picture it. What would entail? And here is the finally. Well, I already wrote that, and now is the time for us to compute some basic integrals. So the first thing I want to compute here is the volume of this room. That will be the simplest possible problem that you can ever see. So let's compute the volume of this room we are sitting in. Of the room. And I think last time we said that this room was like 35 by 35 by 10. I think I counted these tiles. 7.5. No, it was 35 by 30. So 35 on x-axis, 30 and 10 feet. So that was the Now you know how to compute the volume, right? All you need to do is what? All you need to do to compute the volume of this is set up a triple integral, right? So, of course, you have the dimensions of the room, right? So all you do is you set up a triple integral. Actually, no. First, you draw the shape, because then you understand the room better. So you have your good old xy axis. So this is, let's say, 35. That will be your 30. And then it's going to go up 10. So this is how it looks like. There I say we see that on the x-axis, on x-axis it goes 0 to 35. So that's dx, the outer integral. You set up 3Ds, right? You do d, and then you figure out x, y, and z, which way they go. Then you say, okay, so y, which is the middle one, goes 0 to 30, and then z goes on the inside 0 to 10. Remember that we are not putting any function in, because we are only computing the volume. By having 3 integrals, you already have the volume. So now we integrate the inner integral first, which would be z computed from 0 to 10. We still have dy dx to deal with. And that gives you the double integral 0 to 35, 0 to 30 of 10 dy dx. Then you're integrating y. You will get 10y computed from 0 to 30. You still have dx to deal with at the end. So 0 to 35, that's 300 dx, and integrate. This is the Calc1 integral, so 300x from 0 to 35, which is 105 and 2 zeros. Feet cubed. So 10,500 feet cubed. That's the proper way to find the volume of the box. Or you can just multiply 35 times 30 times 10, which is actually what happened. Do what?
Kindergarten is not one.
No. This is the middle school material. Middle school material.
Kindergarten learns multiplication.
Yeah, kindergarten needs to figure out multiplication first. You're right.
Well, integrals are just sums, right?
Yeah, which is addition, so we're good to go. But they do contain times dx, so you do have to have multiplication in order to understand integration. So I think by middle school we're good. Right, everyone should know integration. Oh, yeah, because they know multiplication table by that time. They understand that 2 times x is x plus x, right? Cool. Great, this is how you find the volume of the box. Now let's see what kind of wonderful examples we can get. Okay, so let's figure out some stuff. They do have some kind of wedge on the next example. I'm going to change this problem because I would like to know what is the volume of the door stopper. You know, the little wedge door stopper. So let's see how we are going to figure that one out. So say you have I'm going to make this problem up. So the wedge. I'm going to put that wedge here. It's going to go up. So there's the wedge. A door stopper, right? We understand that that's that. Let's put some dimensions on it. Let's say is 1 inch thick, maybe 2 inches tall, and 5 inches long. Would that make a good doorstop? I guess. I don't know. Maybe we want it to be 2 inches. Let's go swap these. When I think about it, it should be fatter, and it doesn't have to be too tall, right? Inch. It's fine. I was gonna swap those for, I would say, more realistic feel. Cool. So what do I have? I have a shape that I need to find the volume for, and I have my region R. This base here is region R. Now we see that thing is a rectangle, so at least on our setup that's gonna be easy, right? Because we go 0 to 2 on dx, and we go 0 to 5 on dy, so that's a joke. Now we know it's a dz here on the inner integral, and the bottom is flat, and it's on the xy plane, so it's 0, the bottom. Now what's the top? It's a plane, right? The top is a plane. What's the equation for that plane? Planes are linear objects. Anyone mentions a square or a square root or anything like that, can't say it, but
Square root.
so we have to figure out the equation of this plane. Now, which way you're gonna do that, I don't care. You maybe know how to do this, easy way, or maybe you know the hard way. The hard way would be pick 3 points, do the vectors and the dot product and all of that stuff. That might be fun for you to practice now. So, do you have 3 points that are easy for you to see? There is definitely a point 0, 0, 1. There is definitely a point 0, 5, 0. Very good. 0, 5, 0. And pick another one. You can pick this point, right? It's on the plane. It's 2 on x, 5 on y, and 0 on z, right?
And then don't you do like from A to B and then from A to C?
You get the yes, you get the vector here, a vector for this line, and then you cross those.
And then you plug them back in as the coefficient to x minus part A.
Which is, if you go from there and there, then that's that point.
So,
Oh, I get.
thank you. I need to be told this.
Let's do the longer way. So let's see. Let's get this cranking. See how this plane works. The equation of the plane.
While we still know the normal vector, k is always like
2 5 block maximum.
That's probably the only thing I know how to do. I'm just kidding. That was my section on the test.
Okay.
I picked that.
So, what's your game for the one?
I want to think of the other one.
It's a consumes a couple of periods, so if you only need 2 games, you'll get some more.
Looks cool.
I remember reading those.
Did you get the equation of the plane? Z equals
Got 1 minus 1/5 y minus 1/2 y.
no 1/10x. It's just what you said before without 1/10x. It's flat in terms of your plane would be slanted to go through 1 on z, 5 on y, and 10 on x, if you have that 1/10x. No x at all. No x at all, because it is the plane is parallel to x-axis. If you look at the plane, right, x-axis doesn't touch the plane. It runs parallel with the plane. So in that essence, the plane is infinite in that direction. So it's 0 to 2 that will cut off the plane to go between 0 and 2. So the surface here, the plane is z equals 1 minus 1/5 y, and that's it. Now, how do I know that without actually going through all of the nightmare you guys are going through right now with products and so on? Well, I look at this object and I say that if I look at the YZ plane, I see a line that goes like that. What's the equation of that line? Equation of that line is going to be z equals my plus b, which is the intercept. I see it goes through 1, so plus 1, and I need to find m. M is rise over run. I'm treating yz as xy, so it's gonna be rise is 1 unit and run is 5, so it's 1/5. And then I decide not to put any x's around. Oh, sorry, and it's negative because it falls down. So I decide that there's no x needed because it doesn't cross x-axis anywhere. It runs parallel to x-axis. And I know that, again, from extrapolating from the very basic equation, like x equals 3 is a line that goes like this, and you see there is no mention of y at all, because it runs parallel and it will not cross it. Equation y equals to -1 is this equation here running parallel to x-axis, and there is no mention of x in this equation at all. And then any time when, and I learned quickly in mathematics as a form, as a rule, that if one of the dimensions of axis is not mentioned, the object runs infinitely along that. So if you take a look at the equation for the cylinder, right, that goes along z-axis, you just write equation of a circle, but if it's in 3D, it's a cylinder, because you're just explaining this, and z will be infinitely running up and down. So for me to write this equation is just a look at it, and the headache is when it touches all 3 axes, right? But if it's only touching 2 axes, it tends to be easy. So 1 minus 1/5 y. And now we integrate that. 0, 0, 2 to 5. Integrate this is going to be 1 minus 1/5 y. You have to put in parentheses because it needs to be multiplied by dy dx. Now we integrate again, and we get y minus 1 over 10y squared from 0 to 5. Still have dx to deal with. 0 to 2. Now plug in 5. That's 5 minus, that's going to be 25 over 10, which is 5 halves dx. So you're integrating 5 halves, which is 5 halves x from 0 to 2. And you're getting now 2 and 2 cancel, so it's 5. And you go, of course it's 5. Because if you take a look at this wedge, and you put another wedge on top of this wedge, it creates what? Yeah, it creates a box, right? Which is 5 times 2 times 1 is 10. Half of that is 5, right? So it has to be good. That part over there is called mathematics. And some of the European training too. So we were able to calculate this. Now we can make this interesting if you take a round piece of cheese, right, whole, and when you cut the wedge out of that one, it's going to have this part over here curved. There's not going to be a right angle here. So this piece over here, the top, is going to look like a pizza slice, right? With the crust being curved. You don't get to compute that here. You get to compute that in the next lecture, because next lecture teaches you how to incorporate polar coordinates. You use the theta. So if you cut out, a slice of cheese that is 30-degree angle, pi over 6, you get the outer integral to be 0 to pi over 6 on that. And that's going to be the next class when we deal with stuff that is circular and might have it. So you can still compute everything, but this was a doorstop. It was good enough for us to work on. You have a similar problem worked down in textbook, which was oriented in a different way, and they are explaining it for 2 pages. Okay. The next object is the one that we already solved in class, I believe, last time, which is again like a football. I did that for 2, and some various crazy shapes. The average formula. So let me just write the average formula, and then we are going to pick some problems from homework to do, because this is a little bit tougher. So F average would be 1 divided by volume times the triple integral over region R of f of x, y, z dv. Guys, you've seen this formula for everything. Single integral, double integral, triple integral, no difference. Just have to be very cautious of the region. All right, so when can you swap? You can swap if you don't have the function in limits. Now, the trick is, it goes like this. You got A, B, C, D, E, F. Swap at will. Just make sure you match z with z, y with y. So if it was x on the first, and you decide to put that as the most inner integral, then dx goes to the most inner integral. So you have to make sure, swap at will, but match x with x and y with y and z with z. Now, if you have A, B, C, D, and on the outer you have G and H, swap first 2 at will, But if you want to swap the one that has functions in it, you better be prepared to do a lot of work to first get how the object looks like from what's given there, and then when you change the order of integration, see what the new shapes will give you for new limits. Because if you try to swap the age g to enjoy, and I would actually first invite you to try and change order of integration for the wedge, because that would be an easy problem to try and swap order of integration. Because for the wedge, you can make the back wall to be your region of integration, and if you do that, right, then the integral, you will have triple integral. The order of I'm not gonna fit there. You would have a triple integral, and then the order of integration would be, now remember, your y and your z are now your base. So you're taking this wedge and you're putting it on a side rather than having it the right side up to stop the door. So if you flip it on a side, then the shaded side becomes your domain, your region, and that's a triangle. So now you already see that if you draw a dy rectangle, which I'm going to actually use, let's use black. So if you put dy to be the boss of the problem, which would go all the way on the end, that would have c and d as limits, but you can see immediately that your dz, which must be the inner one, right, the middle one, dz is going from 0 to whatever the line is, in our case 1 minus 1/5 y. So that goes 1 minus 1/5 y goes on the middle integral, and then you have dx, and dx goes 0 to 2. So you can swap, but you have to think, and you have to, right? Guys, this is practice. I'm erasing this because it looks ugly and, you know, it's not a part of the previous problem, but you have to think, and you are starting setup from scratch every time. You don't get to recycle anything, because as soon as you change the way you look at the object, you are changing how base of that object looks like. So the first two integrals are immediately different, and then you are changing what functions are on top and the bottom, which means z is different. So the integral that I had over there has to compute 5 still, because it's still physically same object. We're just looking at it from a different way. It would be much better if you all had a 3D printer at home and then you print something and then you can, right, mess with it. But still, with Mathematica, you should be able to graph this thing and then turn it in space and look at it. And you want to always remind yourself that you're shining the light from the top. So in its vanilla state, when I shine the light from the top, it's going to have a rectangle on the base on the bottom. But if I flip this on a side, it's going to be a triangle. That means that the first two integrals, which are describing the region over which the shape exists, is going to be triangle now. So you have to involve a function. There is no way to have just numbers, because 4 numbers on a double integral are always rectangle. So one of them must be a linear line, because you have a triangle, or maybe 2. You know, you can have much worse triangles, right? In this case, like this, you have one function here, one function there, and you have your y-axis going from 0 to 3. And then you have 2 z's. So you can have different types of and as a rule, do not assume symmetry. Damn, I missed that on the exam. I wanted to be fancy when I was taking Calc 3, and I saw the symmetry of the region, and I said, me being lazy, you know, I'm just gonna do half and multiply by 2. Hell no, it doesn't work. It works beautifully in Calc 1 because you're on a one-dimensional input, right? So you're worrying about the symmetry of the function. Over here, the symmetry is captured in the shape. Your umbrella is radially symmetric. It's awesome. The wedge that we did is not symmetric at all. It's symmetric if you cut it this way, right? But if you cut it this way, there's much less volume here than on this side, right? So you don't get to exploit symmetry, you know, easily in these shapes. So I just say do not assume symmetry. If you are good with it, sure, go ahead. But do not assume symmetry by looking at the region R. I'll put base. Because if base is symmetric and you assume symmetry, the top, the function, the actual shape might not be symmetric. And that will ruin your problem immediately. Don't do that. So the next problem for us to solve in class would be problem 16. Problem 15 looks pretty much the same as wedge, and you know how to do that stuff. Now let's take a look at problem 16. It's a really interesting problem, I think. You will have, I don't know, I would see this as a skateboard ramp or something where you can, or maybe not, I don't know. So I have you know what? This looks like a mouse, okay? Almost like a mouse. See, if you look at this mouse that I'm holding in my hand, imagine that this part over here where the cord is going into a peak, a spike, right? That would be the origin of this picture. And then I can put my hand, this is the flat part, right? So imagine it's almost like a mouse, that shape. The surface on top is z equals sine y. Observe the x, remember, parallel to x, the shape. So technically you can draw another one over here, right? The same thing. It will be, it goes forever. And this face over here is y equal x. And this point over here is pi 0. And this point over here is 0 pi 0. So try to set up this monstrosity. You have to pick the order, right? dx, dy, dz, dy, dz, dx, dz, dy, dx, whatever works. Unfortunately, I can't zoom in, and Control plus doesn't work. So so I'm not sure if it's better for you guys to look on the screen where you actually have two colors, or my drawing. I don't know. My drawing is larger, but over there with shading you see how the shape looks better. I wish I could enlarge it.
What is y equals x equals?
It's the side of the, so that will be this. I'm not sure if it will help if I colored region R. What happened? Pi pi 0. And 0 pi 0. And 0 0 0, right? Origin. Yes? Now your shape is symmetrical as e equals sine y. So you're good.
So this
A beautiful wonderful.
Oh, oh my god. Yeah. I forgot about that. I just wrote those down.
There it is. Ah, you're good.
Okay. For oh, yeah. Mhm.
Wait, you can't tell?
Yes.
values. Yeah.
Oh, you put the 5. And then there's 5, 0.
Yeah,
There's nothing.
Okay, so you
Oh no, they can't. Not yet. Because then we talked about like. So if we were to add a function right here, then we would be talking what? X to the power. Because there's a second pi there, right? There's the second, right? I have a question. If we were to put a function right here, then we'd be talking about like.
This is just gonna give you the bond.
So this is almost like doing the double integral.
Oh yeah, no, this is exactly equal to double integral with the function.
Yeah.
The function inside would just be sine y. All right, let's take a look at this problem together. I'm going to draw a representative rectangle dx, which is going to be parallel with y-axis, perpendicular to x-axis. And that's my dx, which means dx goes on the outside, and you hopefully can see, because that's, let me just extend this a little bit. Over here is pi. This delta x would be swiping all of this between 0 to pi. So 0 to pi on the outer, because delta x starts, I'll erase this, it starts at x equals 0 and goes all the way to x equals pi, which is a point. So it will swipe all of the stuff inside. Then we are moving one in, which is dy, because as soon as you put dx this way, you see that the dx is stuck between y on the top and y on the bottom. So this line here is y equals x, and this line, which is on the bottom of the representative rectangle, and this line over here is on the top of representative rectangle, which is y equals to pi. So 0 to pi. And now I have the green bottom of the object, which lays flat on the xy plane, so it's 0, z equals 0 plane, and the top z equals sine y is given to us. Yes.
You said for that center integral is 0 to pi, 0 to x.
No, it is x to pi, because 0 to x. Okay, everyone, please look at the screen now. This is your 0 to x, right there. Okay? That's 0 to x. So the purple one is 0 to x, and the black one is x to pi. Purple one is 0 to x, and the black one is x to pi. Now, what do you do with this in your head? What do I do with this in head? I take the XY plane the way I've been staring it for the last 20 years, which is like this. Well, in your case, for last 10 years. And then I draw y equal x, and I put pi over here. And then I realize that this is my green thingy. So it's either 0 to x, or the black one, x to pi. You're allowed to bring your region and put it, so you're not looking at it sideways. It's lost. Are we all green with this? Yeah. To some extent? I mean, nothing that few hours at home won't fix, but, at least I want to feel good about, myself for a second. You'll have to walk around the table. That's not going to work that way. Or that. And now, so I'm going to erase the pink ones because they are not. Is this pink or purple? What the hell is this? Pink or purple?
That he's right.
Okay, for people who see and talk in 16 colors, should I call this pink or purple? Pink, right? Purple? All right, thank you.
It's a magenta.
Magenta is a name of a child that will be changed when the child reaches 18, okay?
It is a shade of hair dye that I
That's technically what it is. Don't give me a color.
I have the same issue with my calculator.
That's purple calculator. That's a purple calculator. Yeah.
Emily would call it pink. It's a shade that I have. Oh, yeah, that is not pink.
Why are they doing this?
It's pink because I want it to
Let
be.
you weigh gold.
I think that's more pink than that.
I will quickly compute this so that we can move on with our lives. Integral of sine y is negative cosine y, and we are computing that from x to pi dx. So now when we plug in values, I still have 0 to pi to deal with. Cosine of pi is negative 1, and then a negative there becomes positive 1. And then minus and minus makes a plus cosine x over here. And we are supposed to integrate this dx now, which gives us x plus sine x from 0 to pi. And the whole thing becomes pi because both sine of 0 and sine of pi are 0. X equals 0, right? When x is 0 is 0. So the only one that survives is the pi when you plug in pi for x. So the entire calculation works that way.
I got the same answer. I probably did it wrong. I got the same answer, but I had 0 to x instead of x to pi.
Would they? Oh yeah, they would. That's called luck. So this would be a terrible exam question, for instance, because even with the wrong setup, you still get. Like you want that y equal x to be like 2x. So the area that you get and the area that we get would be 2 times apart. Z equals sine of y is the same as y equals sine of x, except it's on the other, right? So it gives you, those metal roofs that are like this?
Yeah. Where do you?
On metal roofs for industrial complexes, they are not used. They're not used into. So you will see them on commercial garages or something like that. They are wavy. So made out of metal. It's not. Yeah. Cool. So that's that.
Thank you.
Look. Okay, next problem. We can talk about another kind of a wedge. We can talk about there are these. I mean, there are many cool shapes. We can set, you know, most of them up. We can do. Let's do another one. So problem 19 and 20 pretty much the same. Problem 18 is the wedge that we already did. So here's the menu of things. We already did 16. So you see the other shapes. This is what? This is a cone plus the ice cream on it, right? It's just squish it. By the way, Paul cup is open, so should feed it after one of the classes. All of these shapes. So let's pick one of these shapes. Do now, whatever. 20, 21, 22, 17,
21.
21 it is.
Then I speak for everybody. When I say 21.
Yeah. It looks like a flying saucer, right? Awesome. All right. Do it. What are you waiting for? It's right there. Just do it. Let your dreams be dreams. Tomorrow is the day. Whatever.
Just do it. Oh, Emily. The
21. Yes, 21. I will draw.
If you don't want to have class, just mention government conspiracy theories for aliens.
He doesn't like conspiracy theories.
Oh, my
My
favorite
eyes
one.
are trying to read that from over here.
Oh, is that
Oh, you
So-
know what? I have it pulled up on my service.
There you go.
I'd like to know how
That'd
to
be
do
smart.
I think you
I'm
should
literally
let
looking at it. See, I'm doing two tests.
So the flying saucer problem. We have a solid between the top piece is the sphere given by x squared plus y squared plus z squared is equal to 19, and hyperboloid on the bottom given by z squared minus x squared minus y squared is equal to 1. Exactly. So we're going to have a shadow, which is some kind of a circle. And you gotta set this up and figure it out. Let's see what you get. Today, please.
Honestly,
No, today.
it's easy. X squared plus y squared equals y squared. X squared equals k plus x squared. Back up that way. Yeah, that's what I was gonna say. Yeah. You got both on the other. You also need both ones. Have fun, guys. Enjoy the other side. But what happens to these kids? No, look, if z squared is equal to x squared plus y squared, then x squared plus y squared is equal to y squared. Oh. Could be r squared. If it was 0, but they were all Just double check if it's 0 and 0. No, it's zero. Yeah, I'm not sure. What am I saying? It's the next chapter. Oh, right. One, of course. No, we're not allowed. Where's this song? And then we're gonna learn the next chapter that is. It's fun. You know what? I think
Right. So let's take a look at the evilness of this problem.
yeah, thanks.
We will start with first figuring out what we have in the domain, which is a circle, unfortunately, right? Not friendly for integration at all. Now, good practice is to draw that circle on a side and you put representative rectangle. Now you want to know what is the radius of such a circle, and the radius is 3. Radius is 3 because we will set two equations equal to each other. So you solve the top equation for z squared and you get 19 minus x squared minus y squared. And you solve the bottom equation for z squared, which will be x squared plus y squared equals to, plus 1. And then you will set the equations equal to each other because z squared is equal to z squared to obtain 19 minus x squared minus y squared is equal to x squared plus y squared plus 1, from where you see that 18 is equal to 2x squared plus 2y squared, from where x plus y is 3 squared, right? You can figure it out. Factor out 2, divide 18, you'll get 9. So we have 3's all around. That's a 3, that's a 3, that's a negative 3, that's a negative 3. So when I draw my representative rectangle, I see this object is symmetric, so yes, I could abuse symmetry for this once because it's radially perfect, it's perfectly symmetric. But I'm not going to. I'm going to see that this representative dx moves from negative 3 to positive 3. The inner one, dy, moves from the bottom half circle, which is in red negative square root of 9 minus x squared to positive square root of 9 minus x squared. And then finally dz, which is the bottom shape solved for z on a lower limit, which means z equals to square root of x squared plus y squared plus 1. And then the top. I don't need the z equals, I just write the square root. And then the top would be 19, square root of 19 minus x squared minus y squared. So who wants to integrate this? No one. That's a very good answer. That's appropriate answer. No one wants to integrate this. This is not the integral to be computed in x, y, and z. What happened? Yes. This is where we will swap into cylindrical coordinates. Cylindrical coordinates will be r, theta, z. And you will transform this integral into a very simple joke of the integral, which would be, we will see this in the next lecture, 0 to 2 pi on theta, 0 to 3, and then this one would be square root of r squared minus 1 to square root of 19 minus r squared dz r dr d theta, and it's a joke to work with this from that point on. You guys are going to have a u sub, and so this is, we did the problem to set it up, but you really do not want to grind through the trigonometric substitutions and whatever other horrors that this integral would bring, because it's not designed to be done that way. We can just simply convert to cylindrical integral, and that is what we are learning on Wednesday, how to do this. So you will do the class prep, and this was an awesome problem to end the lecture, because you've seen, right, you've seen the shapes that are supposed to be done in x and y, and then you see also the shapes that are supposed to be done in other coordinates that we are going to learn next time. So again, anything can be set up in x and y z coordinates, but you are not supposed to compute everything. So if you are looking at the problems on page 1003 and you're looking at these, there are two shapes, problem 17 and problem 21, that are better off to be computed in cylindrical coordinates, which we are going to do next class, where all other problems there are definitely set up and do as x, y, z, and integrate and so on. So here's a little bit of e's and ln's, right? We have that going on for us here. More of the parabolas and planes and everything else. So a variety of these problems. But then, you know, you might want to take a look at some other shapes that, you know, are lying around the house. Measure them. Put them in a 3D system. See if you can figure out the volume. And then do the water displacement to see if they're actually, if you got it right. So if you have a solid object where the water can't come inside, right, and it's edgy like this, measure it, figure out the functions. So that's how you play with these things to actually become engineer one day, to actually use it. Because, as I said, I can't care less if you can integrate You will never do that once you. But if you can't set up this integral, your value on the market is 0 because machines can't do that. Mathematica or MATLAB or whatever the hell you want to use is not going to look at the shape and set up the integral. That's your job, to figure out the volume and all of those things. You will take whatever we have on the screen once you set it up and put that into Mathematica, and Mathematica will integrate for you. So, yeah, and also look up how to put into Mathematica double and triple integrals so that you can have that for your lab that it's coming up, right? Lab number 3. We should start on that, and then you will obviously do that next class. All right, so that's it for this lecture. And actually, now that I see I can actually work on the next lecture, let's take a few moments off, and then we'll, I guess, restart the stream. My stream.